I'll start with feeling the room a bit. Who has heard of DevOps? Okay, the majority. Who thinks he has a rather concrete idea of what DevOps is? All right, let's give it a try. What do you think DevOps is?
So, combination of your development and operation. So, you have your CI setup, you have your development, you push everything, install, maintenance, what you have to be tested, verified, gains back. If something's not right, well, only testing, and then continuously testing.
Yeah. Okay. Maybe you can give the presentation. It's a nice summary indeed. So mainly what is it about? It's about short iterations, short cycles, lots of continuous testing. Basically, in general, making sure that your master branch is ready for production at any point in time. Okay, that was the presentation. No. So let's go a bit deeper. So first off, why should you care about DevOps at all? It's mainly because of these numbers. So what I do a lot is, when I start a new project at a company, is convincing people that it's actually worth to invest the effort and time and money into implementing DevOps principles and initiatives. So these are numbers that tend to convince people quite easily. So at a quick glance, you see big numbers, so it must be good, right? So 200 times more frequent code deployments between who and who, we'll see later on. 106 times faster lead time, 2,600 and so many times faster time to recover from a major incident, and 7 times lower change failure rate. These all seem like very interesting metrics. Looking at your own projects, I guess you can have an idea on what is our frequency of code deployment, how many times do we, if we push something to production, how many times do we have an issue actually after pushing it? And then think about these type of margins that you could get if you implement DevOps in a good way. All right. So, small table of contents. We will first zoom out, look at what the hell is DevOps actually, where does it come from? Yeah, okay, I can try that. I tend to do that. Does it work? Okay. So we'll first zoom out because something that people might be confused with is DevOps is not about tooling. So DevOps, people think about DevOps tooling, they think of Docker, Jenkins, Kubernetes, I don't know, microservices, AWS and these kind of things. Yes, all of this are ways of enabling DevOps practices, but it's not actually the core of what DevOps is about. DevOps is about a certain mentality on how to run a project team, and we'll first talk about that. Then we'll zoom in and see, okay, if we apply those principles to a day-to-day environment in your development environment, what kind of lessons can we learn from applying those principles? And we'll make it concrete on actually what to do. And then lastly, in the zooming in part, you will see there's a bunch of things we could apply. First question people have is, okay, where the hell do I start? Like, this is such a big change from what we are doing right now. Where do we start? And yeah, we'll see. Okay, so first off, the data. So these data points, they seem unbelievable. So first off, I'll try to convince you that they are real data points. Yeah. Okay. So they come from the State of DevOps reports 2012, 2013, up until 2019. What are these State of DevOps reports? They're created by DOR, which is the DevOps Research Association, and also by Puppet, which is a rather large player in the DevOps tooling community. They are scientific studies that span over 7 years, 7 years from 2012 to 2019. And in these 7 years, they now have over 30,000 survey responses. So actually, this is the largest data set in the world on these kind of practices. So the nice thing is that we are looking at data-driven conclusions, not just people's feelings or gut feeling or whatever. It's really like, as an engineer, I tend to enjoy we measure it and we take the conclusions from the measurements. Okay, so it's also, if you're impressed by these kind of things, it's also sponsored by all of the big boys in the industry. We have Deloitte, AWS, Azure, GitLab, Atlassian, and plenty of others, Google Cloud. It's also, the research is reproduced and backed by third-party research by big names in the research community like Forrester, Gartner, Capella. It's also not only for Googles and Amazons, which is also another misconception people have about DevOps, that it's for big companies who have tens of thousands, hundreds of thousands of developers. Maybe they are developing, I don't know, especially with in mind web services, where people need to have 100% uptime or as close to 100% uptime as possible. But actually, it's not only for Googles and Amazon. So if we see here, 36% of the companies are technology companies, so these are indeed Googles and Amazons of this world, but also education, finance, industrials, media, energy, non-profit, basically the whole spectrum is the conclusion. The whole spectrum of companies is implementing this. Also from all kinds of sizes of companies, actually as you can see, the largest portion of companies that implement it successfully, they have less than $50 million annual revenue. And then also, of course, the big boys, they also implement this. And the size, again, so not only in revenue, but also in amount of employees. You see that the biggest portions are medium-sized companies between 100 and 500 employees and over 10,000 employees. And there's a very good reason that it's distributed like this. And that's because DevOps, as we will see later on, the problems that it tries to address, they tend to come with trying to scale up the development of an application or of a target application, let's say. And so for companies with less than 20 people, the benefit is not so large because the friction of not doing it is not so large. But even for the smaller companies, I will try to convince you that there's also a benefit. And of course, for the very large companies, if you don't have something like this in place, either DevOps or something similar, some structured way of organizing your development teams, yeah. We all, maybe not all of us, but most of us, I think, have heard of the mythical man month, where they argue that doubling the amount of developers will only double the amount of friction and not double the output. All right, so what is DevOps? And this is really jumping into it. This is all of this. So DevOps is basically just about a way of thinking on how to optimize a value stream. So what is a value stream? Sounds very salesy. It actually is kind of salesy. But in our context, we can think of a value stream as the process from writing code, pushing it to a Git repository, building it, deploying it, and getting it to the customer. So in the end, it's the whole stream between you as a developer writing some code and it delivering value to the customer when it's really running on target or whatever. So first step is identify your value stream. And this means map out all the steps that you currently have in your development process that sits between you writing the code and it running in production. Next step is install some feedback loops, and through, as we will see later on, experimentation, we will try to gather data on if we do this experiment with our feedback loop, or if we install this specific feedback loop, will we tighten the value stream, or will we not? On the adverse, will we actually delay the value stream? So in the end, it's about identifying what you are doing, setting some KPIs, doing some experiments, and looking at what the result is on those KPIs, learning, adapting, and doing it again. So it was pioneered by Gene Kim. He's a DevOps thought leader. He's unsurprisingly the founder of DORA, so the DevOps Research Association. And he's also the writer of the highly influential Accelerate book, which I can advise every one of you to read. It's 150 pages, so let's say over the course of a weekend or 2 evenings, you can get through it. And it's basically it's not so dry, because if I'm going to explain it, it's going to sound really dry, but it's statistical analysis on all of these experiments that they did, and then driving the conclusions from there. And basically it gives you a roadmap of with the evidence we currently have, what are the best practices to implement to optimize the value stream of developing software? It's also won the Shingo Publication Award. Do you care about that type of thing? So what is the DevOps algorithm? As I previously said, so we create a repeatable and reliable value pipeline. The repeatable part is important because if it's not repeatable, then if we are making experiments, next time you run the pipeline, it can have a completely different behavior and you actually have no clue on what the impact is of what you did. Second step is we track some KPIs that should quantify the performance of the system. As you can see, the choice of KPIs will be critical here because if you choose bad KPIs that don't really are not really good proxies for your performance, then you will make the wrong conclusions. We perform some experiments applying specifically the concept of if something hurts, then you should do it more often until it becomes painless. An example would be in an embedded environment, typically what hurts is integrating all the different parts of code that different teams wrote. So in your own team, you probably have a reasonably good way of handling problems. You just talk to each other and you fix the code. But then if you integrate with other teams, typically that's where the problems start popping up. So if this integration is what is hurting, instead of what companies are doing sometimes is this is a really difficult step. Let's delay it as long as possible to do it. No, the DevOps principle is just to do it the other way around. If it's difficult to do, we should do it every day. So it forces us to find an elegant solution to the problem. Then fourth, evaluate the impact on the KPIs. Learn your lessons from what you saw the effect was on the KPIs, and then go to 3. So while true, steps 3, 4, 5. So the bottom line is improve both the speed and quality of your outcomes through permanent experimentation and evaluation of the results. I would say that's in a short, the engineering principle of measure it and you know what the impact is of something. So what are the classic DevOps KPIs? Actually, these, how does the tracking thing work? Yeah. These 4 are the classic ones, and this one is a relatively new one, not really applicable to every situation. I would say for an embedded system, availability is not as important. It's more specific for web services and so on. But the 4 that we should think about is lead time and deployment frequency, which is about software development. It's about velocity of software development. And we have change fail and time to restore, which is about software deployment or the quality of your software. So what makes these 4 metrics? Why should you trust these? So in all the research that they did in the DORA initiative, they found that elite performers were found to be at least twice as likely to overachieve or at least achieve the following objectives. So a quantity of product or service produced, efficiency, satisfaction of customers, quality of their product, or basically almost any organizational or mission goal that they had. People who had a good implementation, an elite performance implementation of DevOps were twice as likely to hit these goals than organizations that had low DevOps performance. So is it, the surprising conclusion also is, surprising, depends on whether you know about it or not. Quality and velocity go hand in hand. So what some companies tend to do is, we are way too slow with releasing, let's stop testing and let's push code to production. Or the other hand, we have so many problems with deploying, let's slow down the development and really focus on the quality. Apparently, when looking at the data, these things tend to go hand in hand. So either you're doing a good job at organizing your deployments or you're doing a bad job, but you can't just focus on one of the 2 aspects, they're correlated. So high performance, what are we talking about? What are low performance, what are high performers? It's a bit of abstract reasoning, so let's look at what the data tells us. And also you should realize that this is a sliding scale. So every year again, they redefine high and low and medium performers according to almost normal distribution. So what is a low performer last year, or let's say what's a high performer last year? If they don't keep improving their process, next year they can be a low performer if they stagnate. Okay, that's aside. So in 2019, Low performers had deployment frequencies between once per month and once every 6 months. If we go back to 2015, low performers were deploying between once and twice a year. So already the low performers, they increased a lot in their deployment frequency. So 2019, low performers once per month, or between once per month and once per 6 months. Lead time for changes. What is lead time for changes? It is, I'm typing some code and I push it. How long before it gets to the customer? Low performers between 1 month and 6 months when you check in some code into Git before it gets to the customer. Mean time to restore. What does it mean, the metric? It means something happened in the production system. It crashed or whatever. The definition of failure is that it is no longer delivering value to your customer. So if it partially fails, but it still gives value to the customer somehow, it's not considered in this metric. Between 1 week and 1 month to restore from one of these critical crashes, let's say. And then how many times does one of these crashes occur when we push a new change to the production? For low performers, it's about 50% of the times that they push something. Medium performers already a lot better. Between 0 and 50% change failure rate, less than a day for mean time to restore, between 1 week and 1 month lead time, and between once per week and once per month deployment frequency. And as you see, they go up and up. The elite performers, they have on-demand deployment frequency, which means basically you push code and immediately it gets deployed. Lead time for change, less than 1 day. Same thing, you push code, immediately it gets deployed, almost immediately it gets to the customer. Mean time to restore, less than 1 hour. Change failure rate stays the same because it's already very low. If you go back a couple of years, this would look a lot different. But yeah, basically from medium performance on, you tend to have very low failure rate. Now maybe you're already thinking, yeah, as an embedded developer, pushing code to the customer multiple times a day, it's not gonna happen. Indeed, it's not gonna happen. But to get the benefit that the elite performance have, you can basically simulate the behavior of deploying to the customer by deploying to a running target at the same frequency. And if you then have user acceptance testing or something, you can get kind of the same results as you would with people like Amazon who deploy, I think, what is it by now, 1,000 times a second or something, they deploy a new version. It's an unbelievable metric. So yeah, you will never deploy multiple times per day to a running system, I mean, at the customer side, but you can simulate those conditions locally. Okay, so again, conclusion, between the low performers and the elite performers, 208 times more frequent code deployments, over 100 times faster lead time, 7 times lower failure rate, and over 2,000 times faster time to recover. Seems interesting, no? Maybe we should learn a bit more about how we can get to these numbers. So, as I said here, should have thought about this. Install feedback loops and perform experiments. So people have been doing this DevOps thing for quite some time, and they have been sharing what experiments have worked and what experiments haven't worked. So let's learn from the mistakes and successes of other companies, and let's look at what experiments have succeeded in improving their development frequency and all the other metrics. So on the one hand, we have business practices, self-driving cross-functional teams. They tend to greatly improve your production speed. Why? Your development speed. Why? Because if you don't have cross-functional teams, it means that you have to interface with other teams to basically perform your value stream end-to-end. So let's make this more concrete. What does it mean? It means if you're a developer and in your development team you don't have a tester, and you don't have someone knowledgeable about deployment and operations, for those aspects of the value stream, you will have to interface with the teams that have these people. And every time that you have to interface with someone outside of your own team, you will find friction in communication, different schedules that people have, different priorities. Maybe their manager is pushing on them to not take on new responsibilities, who knows. If it's all in your team that it happens, it's basically as frictionless as it could be. If the guy sitting next to you is doing the testing and the guy sitting in the back is doing the operations, then all of you can sit in the same room and problems can be easily fixed. Lean product management. What does it mean? Small and frequent releases. Yeah, that's what we're going for, so obviously it's helping. And continuously gather customer feedback and quickly learn and adapt. Again, it's in the same line of thinking as the previous process we saw. And then transformational leadership, which is a fancy term for basically leaders who give their people the responsibility in the field, let's say. So instead of pushing decisions top down, they allow room for people to have their own opinions and to think of solutions themselves. Okay. Those are the business practices. If I give this presentation to a bunch of managers, I would dive deeper into this, but I'm not, so let's not dive deeper into this. We're here for the technical shit. Continuous delivery. What is continuous delivery? It means automated deployments, automated testing, continuous integration, Turnbased development, version control, everything, and so on and so on. The idea is that you have a completely automated build system that grabs your code from version control, builds it, eventually packages it if it's needed, and pushes it on target. So everything that you would do manually in this process is completely automated, which means that the only manual action you need to take is to write the production code. All of the rest is handled automatically by something like a CI system, like Jenkins, Bamboo, whatever suits your boat. Loosely coupled architectures. Loosely coupled architectures, I had a slide here that. Loosely coupled architectures, it means in web development or web applications, you would think of microservices. But you can also apply this to embedded development. If you're running embedded Linux, you can develop applications that are using a service type of API on the device. If you're running bare metal, this basically means that the different teams working on different modules of the application, they should not be tightly coupled with each other. So it means that you have cleanly defined APIs, and outside of these APIs, in people's modules, they get to do whatever they want as long as they don't break the API integration. And then lastly, ruthlessly automate everything, and we'll also go deeper into this. So let's look at each one of these technical practices. Continuous delivery. So when they were doing the research at Dora, they had to define all of these practices to actually be able to measure them. So they defined continuous delivery as the following two aspects. Teams can deploy on demand to production or to end users throughout the software delivery lifecycle. So it means we don't need to wait until the sign-off to push to production. If we are certain that our code is stable, we can push it to production without needing any kind of formal approval to do so. And secondly, we get fast feedback on the quality and deployability of the system, and it's available to everyone on the team. So this fast feedback has to be, the feedback has to be fast, it has to be available to everyone on the team, and people have to actually care about the feedback, and they have to, if something breaks, they have to make it the highest priority to actually fix it. So in reality, this means you have a CI system, that runs tests, the tests have decent coverage, and if the tests fail, or if the CI system gives you some feedback, you actually take it into account. It all seems kind of obvious, but in reality, it's hardly ever the case. So what actually affects continuous delivery? Test automation, which actually has the highest impact of any of the metrics. So the more test automation that you implement, the higher the chances that you will have a functional continuous delivery pipeline. Automation of deployment, shifting security left, which means shifting it left in the software development lifecycle, which means instead of after developing everything, you hire a team to come look if they can hack into the system. No, instead during the specification analysis, you think about how will we implement security from the ground up. And maybe to link it with the Rust talk, I think this is kind of the idea for that language actually. Well, not security, but safety. Let's shift it left. Continuous integration, obviously, because who's going to press the button to test otherwise? Turn-based development can be pretty interesting. Who here has heard of turn-based development? Who has heard of Git flow? Same people, okay. So we'll go into that deeper in a second, but basically turn-based development, in short, is instead of having a bunch of branches, and everyone develops on their own branch, and at the end of the development cycle, we merge all of them together. The idea of turn-based development is that turn-based, you could also call it master base or whatever, you have one branch that is the reference branch. Everyone who develops branches off from the master branch, does some implementations, and as quickly as possible merges it back into the master branch so that the different branches, they cannot diverge in the meantime. And then finally, version control, which I hope is obvious to everyone in the room. All right, turn-based development. Here is a nice picture that might or might not make it clearer. So here we have the master branch. And if you want to develop, you merge off the master branch. Here, this example is of releasing. Okay, so let's say you do a release. This release will stay on its own branch and you will never touch it again, except if you implement a bug fix. And if you implement a bug fix, you should also merge it back into master. But basically the idea is have 3 or fewer active branches in your code repository. Ideally, so let's say you have one master branch, at any time, at any point in time, it should not have more branches than the number of developers plus 1, which would be the master branch. Also, merge branches at least once a day. So no branches of 3, 4, 5 days of lifetime. So yeah, if you're implementing something and it takes you 3 days to implement it before you can merge it back into master, you're doing it wrong. Don't have code freezes and don't have integration phases. Basically, code freezes and integration phases are necessary evils if you don't follow trunk-based development, because your branches will diverge from each other over time, and you will need to basically stop the amount of diversion happening to actually get them merged again. So this is more a side effect of not doing trunk-based development than it is the reverse. So what do we get in return? Branches don't drift away from each other because they don't have the time to drift away from each other. If you have to merge in once per day, I mean, that's at maximum 8 hours, let's say, of code diverting from the master branch. You have pain-free merging as a result. And teams become, and this is for me the most interesting one, teams become forced to split the development work into small bite-sized pieces. Because if you have to merge in once a day, you have to also have features or user stories that can be implemented in less than a day. So if you have a feature that takes 5 days to implement, you have to go back to the grooming and you have to groom it into smaller pieces so that you can actually merge it in within a day. So if you have a big feature of 5 days, split it into smaller features with each feature delivering some value and merge that in separately. And then lastly, there's interesting downstream incentives by increasing the dependence on the CI. And what do I mean by that is if you really have to merge in every day, you cannot do a big manual test suite every day for every merge. So your CI has to be able to give you a proper coverage on the testing. Otherwise, you cannot trust it to not break the master after merging it in. So it forces you to follow good practices. What do you have to watch out for? Don't implement a heavy code review process. And people not used to trunk-based development, this will be their first reaction. Whoa, we're gonna push to master every day. Multiple people are gonna push to master every day. Well, we need a couple of senior guys making sure that none of the code that gets pushed to master is dirty code. This will again slow down your development cycle and basically you're back to square one. Secondly, as I already said just now, you have to ensure that you have very high functional and technical coverage in your test suite, as the CI will have the responsibility of keeping the master green. So it incentivizes you to heavily invest in test automation, which is good for my business. It incentivizes teams to run automated tests very often, and it incentivizes fast builds and test runs to get quick feedback. Another pet peeve of mine, test code is production code, because your CI system is in charge of the production code. So you should consider it part of the production system. Why do I say that? Because some people, plenty of people, tend to think that test code, it never gets shipped to the customer, so the quality of it is not so important. And they tend to take shortcuts or write ugly code or not care about the performance of it. Or, I have to set up this big system that takes 20 minutes to set up to run one test case that runs 5 seconds. Yeah, but it's test code, we'll just run it overnight, doesn't matter. No, if you have to merge in every day, ideally it's almost instantaneously. If you push to your Git, if you merge your master branch you want to know as soon as possible if you broke it or not. So again, it forces you to apply the good principles. Alright, that's it for continuous delivery. Loosely coupled architectures. So how did Dora define loosely coupled architectures? Respondents can do testing on their part of the application without requiring an integrated environment. And secondly, the service or component that respondents worked on, it could be deployed or released independently of other services. So what does the first thing mean? It means that you can use dumb mocks that just satisfy a certain API to test whether your service is actually breaking anything in the integrated system. What usually tends to happen is people with tightly coupled architectures, they have to set up real life versions of the dependencies to be able to work. For example, if you have a system that depends on a database, if the database needs to have real live data for your application to function, it means you are tightly coupled to the database. And secondly, deployed or released independently, it means that the different teams, they can have their own release cycles, they can make their own decisions, they don't need to take into account the other team's agenda or backlog or whatever in order for them to make decisions, which again makes it easier and faster to make decisions in your own team. So the bottom line is, how modular is your architecture? So why do we care about this? Because there is a direct correlation between modularity and where your team is situated on the elite, high, medium and low performance index. So, how does it influence software delivery and operational performance? If you have a loosely coupled architecture, you can refactor or redesign the internals completely, maybe handle technical debt, whatever you want, whatever you need to do in your team, without having to align with other teams, or without having the fear of breaking integration. You can work independently, again I said this already, okay. Face fast and painless testing. So, because you have as a design principle that you have loosely coupled modules, it means that your tests can be run with mocks, and it again incentivizes you, well, in the end you will have fast feedback because testing against the mock is much faster than testing against a live system. It allows for scaling up the complexity of the integrated application without increasing the complexity of individual components. Okay, what does it mean? It means, okay, we have a very big application we want to write. We can scale up we can decrease the time it takes to implement it by putting more people on the problem, which is again what people were warning us about with the mythical amendment, that it's not possible. Yeah, it is possible, just not if you all work in one big, tightly coupled architecture. If you can split 50 people in 10 teams of 5 people that work independently, then it can work. And finally, we have the inverse conveys law. What is the inverse conveys law? Who knows what the conveys law is? Okay, you tell me.
I thought that the example was if you write a compiler and you have 3 teams writing a compiler, you will end up with a compiler in 3 stages.
Yeah, that is a very concrete application.
Yeah. It's an example.
Yeah, indeed. So that's a good example. The general law of Conway is, if you're writing software, your software will be mirroring the organizational structure that you're working in. So organizations which design systems, they are constrained to produce designs which are copies of the communication structure of these organizations. So what does it mean? Indeed, as you said, you're working with 3 teams on a single application. If you have a tightly coupled architecture, it will mean that you actually have 3 sub-applications with a wrapper around it. So how do we exploit this Conway's law? Let's apply it in an inverse way. It means that if you want a loosely coupled architecture, you should divide your teams in such a way that their communication is loosely coupled and that they don't need to align to make decisions. So again, let the teams make decisions. We are back to the self-driving cross-functional teams here. If you install these type of teams, you have a much higher chance of actually getting loosely coupled architectures. And then rootlessly automate everything. So if we look at high performers, so this is not elite performers because This was studied in 2017 when they only had low, mid, and high performers and not yet the elite aspect. High performers, they implement 32% more automation on configuration management, 27% more testing automation, 30% more deployment automation, and 27% more change approval automation. This means your CI gets to make the decisions. This means you have a way of automatically flashing your application to your device without having to do any manual steps. This means you don't test manually, and this means if you have configuration in your, for example, in your development environment, instead of doing it manually, you have something like Chef or Ansible or any other configuration management tool to automate that configuration. So you have configuration as code. Okay, so automate everything, what does it mean? What should we automate? As I said, configuration management, which the principle is called configuration as code. Similarly, we have infrastructure provisioning, which is called infrastructure as code. Same idea, just different aspect that you apply it to. So typically things that your IT team would be doing previously, installing your OS, installing your build environment, installing your Jenkins installation, whatever. You should, instead of having a person do this and keep his knowledge in his head and maybe lose that knowledge later on, put it in code, in human readable format if you like, and then if you redeploy it, it will be deterministic. Automated deployment, as I said earlier, integrate flashing your platform and getting the code to run it in the CI. So your CI should also have the responsibility and capability of dealing with your hardware platform. And then change approval. Instead of having manual code reviews, let your CI with some quality gates drive the automated trunk merges. So trust your CI and your test suite to do the merging and inform you if something happens. And finally, if you are doing something manually on a relatively regular basis, put effort into automating it, even if it's not mentioned on the slide. All right, so we've seen the bigger picture, we've seen the details of it. How do we actually start implementing it in our teams? In 2018, the DORA report, the DevOps report, gave us a step-by-step procedure, not to religiously follow, but basically something that the data again supports that it works better than other ways of introducing it. So we have normalizing the technology stack, standardizing and reducing variability, expanding DevOps practices, automating your infrastructure delivery, and providing self-service capabilities. We'll go into each of these in a minute, but just in general, the first two steps are about, so in general, if you look at it from a further perspective, what is DevOps mostly, as you said actually in the beginning, I can't remember who, was it you? The idea was, let's automate everything that we do manually so that we can focus on what we are good at, which is writing code, or let's focus on what the machine cannot do yet, which is writing code. So first off, we're simplifying that problem. So if you have a very diverse technology stack, automating it will be hard because you have to take into account, okay, I want to automate my configuration for Ubuntu. Oh, but wait, my colleague is using Red Hat. My other colleague is using, I don't know, some other operating system. Maybe someone is even using Windows, as I am. It will be much harder to automate all of these operating systems or having a system that can deal with all the variability of your stack. So first reduce the amount of choices people have so that it's much easier to automate it. And then if you need the variability later on, introduce it once you have a working automated system. So first, simplify the problem, automate it, and then make it complexer again. Secondly, standardize and reduce variability. So it's the same concept, but applied to different aspects than just your technology stack. Third off, okay, we finally get to the meat and potatoes. We start implementing the DevOps practices. Then fourth step is we automate infrastructure delivery, which is, once you start thinking on DevOps tooling, this is what most DevOps tools focus on, automating infrastructure delivery, while it's only the fourth step in this process. So why is it? Because it's a rather difficult problem. It's also not really low-hanging fruit. So if you start implementing DevOps, don't make the classic mistake of starting with writing Dockers for everything, uh, maybe using VMs for everything, I don't know. This is only the fourth step. It's not even, it doesn't have as high an impact as the other practices. So it's cool, it's new, it's interesting, I get it. It's also how I started with it, but it's actually not the way to go. So do it in your free time maybe, but first go through these 3 steps before you start doing that. And then finally provide self-service capabilities. It means that, for example, let's take into account Jenkins. You want to run your tests into a certain container, a certain Docker container. Without step 5, typically you would have a couple of containers running permanently and then just deploy provision the test environment, run the test cases and get the results. With self-service capabilities, it means that if Jenkins needs this environment, he will self-provision it, he will set the environment up, he will run the test cases and he will break it down afterwards and wait for a new command to come in. This means that you have theoretically unlimited scaling, because if you then combine it with something like AWS, you can just provision as many nodes as you need, so you will never again have the problem where you're waiting on the test execution of your colleague before you can test your own code. Alright, let's go into it. So normalize the technology stack. What are some typical practices people do also in this stage? Version control for application development, which is hopefully a default by now. Teams deploy on a standard set of operating systems. So instead of everyone having their free choice on which operating system they develop on, you choose a couple, maybe one, ideally one, maybe 2 or 3 OS systems that you develop on. Also this doesn't mean that you cannot use your Windows, Mac, whatever laptop anymore. With the Docker containers that we have, you can just run a Ubuntu container, a default Ubuntu container, don't spend time on customizing it yet in this step. You just take a default Ubuntu container, everyone boots it up and uses that as his development environment. And then their host system can be whatever they want, just use the Docker container as a development environment. You put your application configurations in version control. So it means if you have configuration in your application and you have to configure it manually every time that you install it, refactor your application to take YAML, XML, whatever type of configuration file to automatically put it in a certain state. It will also greatly simplify your testing, because then if you want to put it in a certain state, you just create a certain configuration file for it and it will always get into that state without failing. And finally, it seems rather obvious, but it apparently isn't, because I've seen a couple of companies that don't do this. Share your source code between teams, so that people can have a look at your source code to know whether, if they have to integrate with you somehow, that they don't have to come to you and ask, can I do this, can I do that, would your application suffer if I do this or that? Basically, it's about keeping the control in your own team. By exposing your source code to everyone, people can look for the information themselves instead of relying on you as an interface. And also you can learn from other people's code, but it's not so relevant for the developer. Stage 2, standardize and reduce variability. So not only on the operating system, but also built on a standard set of technologies. Try to use the same build system in every team. Try to use the same CI system in every team. Try to use the same unit testing framework in every team. And so on and so on. Programming language, Misra set even, maybe whatever. If you're using a specific set of rules or technologies in your development team, try to standardize this across the whole company. Single standard operating system, so here it was a standard set. So maybe Ubuntu systems, here it is a specific operating system, so let's say Ubuntu 16.04. Specific configurations in version control and re-architect applications based on business needs. This is where you would start refactoring your application to become more modular if it's tightly integrated. Step 3, expand your DevOps practices. So individuals should be able to do work without manual approval from outside the team. So code reviews from the local company guru, maybe your manager who has to sign off on, yes, this feature can be shipped to the customer, these kind of things, get rid of them, they slow you down. Deployment patterns are reused. So if a certain team finds a very efficient and interesting way of doing something, Don't reinvent the wheel in the other team. Take their pattern, apply it, and if you can think of a way of improving their pattern, do the experiment, learn from the results, integrate it if it's better, and then roll it out to the other teams. So basically, don't only standardize on technology, also standardize on process. Use continuous integration and completely depend on it. So no longer should you have a manual testing team that needs to do the final validation before you push it to the customer. And you can make changes without significant wait times. Basically, that's a side effect of the other practices that you implement. But if you can see, if you find yourself in a situation where you can do this, you can be pretty sure that you did something right. Stage 4, automate your infrastructure delivery. So automated system configurations, provisioning is automated, application configurations are in version control, everything is in version control basically. And if you want to deploy it in a certain state or a certain configuration, you just take a configuration file instead of depending on someone to manually get it into that state. So it means don't hard code stuff into your source code. And basically version control everything. If you have an application that, for example, you have a choice between, what can I think of? Let's say you have your Jenkins system and it can work with GitHub, Bitbucket, GitLab, all kinds of different Git systems. If you have to choose, when you set up your Jenkins, make sure that if you provision it, that it can read from a configuration file which of these systems it will support. Don't just install Jenkins and then have someone manually install the plugin specific for the Git system that you are using. Have it in configuration. For Jenkins it's obvious, it has a plugin as, what is it called? Plugin as code, I think, for plugin configuration. Sorry?
Pipeline as code.
Yeah, not pipeline as code, that's not what I mean, but it's also a good example indeed. So if you write a pipeline, don't just use the UI to click on what the pipeline should be, write it as code, and then if you migrate to a different server, you can just pick up your pipeline and drop it there and it will work again. And then finally, self-service capabilities. Incident responses are automated, so it means if your system crashes, instead of just informing you that it crashed by looking at your Jenkins screen, maybe you can have some kind of automated recovery for it. Maybe it can send emails to certain people. Maybe you have a certain set of problems that you've seen in the past and you know how to solve that problem, then automate the solution for that. Resources are available via self-service, so that's what I was saying about automatically spinning up more VMs, more Docker containers if you need them. Security teams are involved in technology design and deployment. So basically shifting security left. So if you don't have anyone knowledgeable on security in your team, get someone on board. Application developers deploy testing environments on their own. It means that you don't rely on IT or a DevOps team or whatever to write the Docker files for your test environments. It means that you as a team, so not you as a person, but as a team, you have someone with the capabilities of doing so. Again, the cross... Okay, Google. So basically, again, if you need to deploy testing environments, you should have the knowledge of doing so in your team. And then finally, success metrics for projects are visible, and I think I forgot here, to everyone in the team. So don't just, the results of these KPIs, don't just leave it up to the managers to interpret them. Have it open to everyone so that if you did an experiment, this sprint, for example, and you see that the metrics are going down or up, that you can realize yourself, okay, I did this experiment, this is the effect on the KPIs, I should try to do it less or do it more often next sprint. Alright, recap. Why are we doing it? Because these numbers are real. What are we doing? It's a very simple thing actually. Define your system, create a feedback loop, and experiment on it. And then how should we do it? We go through these 5 steps. And in the end we should get higher deployment frequency, faster time to recover. What was it again? Yeah, lower lead time and less failures when pushing to production. Thank you for your attention. I hope you learned something.